This lesson 4, is about indirect measurement of distance. Suppose I need to measure the distance between point A and point B. I can't do that because this big pond is in the way. I physically can't roll out my tape measure between point A and point B because of this pond. So I need to measure it in an indirect manner, using other measurements to somehow calculate the distance between the two banks of this pond. There's a few different ways we can go about doing this. One way is using offsets. So I could, at X, put a perpendicular, since it's at right angles, offset to a point Y. Okay, I can measure this distance, say it's 10 meters. Then I can measure the distance between Y and some point Z. Say it's 50 meters. That will allow me to then use Pythagoras to calculate the distance between Z and X. I'll call this distance, give it a letter, say M. I could use Pythagoras and say M squared plus 10 squared is 50 squared, and then go ahead and solve that for M. Okay, just using the Pythagoras trig that we've detailed earlier. Okay, to find that distance indirectly. We can physically measure the ones with 10 and 50. We can't measure the M because the pond's in the way. Alternatively, we could have done two perpendicular offsets, okay, and just measured this distance RQ and recognize that it would be the same as the distance SP. Okay, just using a little bit of creativity to do these offsets. Another way would be to use some similar triangles. So the idea, if there's a line segment, say this line here with two lines on it, and then there's another line here with two lines on it, it means that this distance and this distance is equal. Similarly, over here with a single line, means that these two distances are equal. How does this help us find the distance between G and C? Well, I have two triangles. One is EFD, the small one, and then I have the big triangle EGC. If I say that this is of length, say 2, and this is of length 1, I'll know that the distance from E to G will be double that, so it'll be 4, and the distance from E to C will be double whatever E to D was. Okay, so this will be 2. So I can see that from the small triangle to the big triangle, everything's doubling. So I could physically measure this distance. Suppose it's 7 meters. Okay, and then I could use that to find this distance. Okay, knowing that since these triangles are in the same proportion, okay, they're similar triangles, they're not the same size, they're similar, I know that the ratio of the sides will be the same. So if I just pick two sides here, I could pick, say, the side GC, and so this side GC and this side EC. I know that ratio is going to be the same as the corresponding sides on the other triangle, like FD on ED. Put in all the values. I don't know GC. EC is 2, and over here FD is 7 on 1. Okay, so you'd end up solving for that side GC and getting 14. Probably think, yeah, that was a bit harder than it probably could have been. Yeah, you might be saying, why can't I just say that the scale factor is 2 and then do 7 times 2 equals 14. Hey, that'll be okay as long as you showed how you found this scale factor. If you showed that scale factor is 2, since EC on ED equals 2 and EG on EF equals 2. Yeah, just to show that that actually is the scale factor of 2. Yeah, but either way, for communication. Final method is using similar triangles. Sorry, correction. Congruent triangles. Congruent triangles are triangles that are exactly the same. Remember all those rules from year 8? SSS, SAS, ASS, RHS. Okay, all of these will come in handy to find congruent triangles. In this case, I know I've got a right angle which is the same. Okay, I know that a side is the same, and I know that these hypotenuses are going to be equal as well. So what we can do is, if I can measure this distance RS, I know it's going to be the same as RT. Okay, RS equals RT due to congruence. So essentially we have to find any unknown side that I'm trying to find just by using the other side on that triangle. So for example, TP and QS are the same. I should have explained earlier, if we put 2 vertices, so 2 of the points together like TP, it refers to the distance along there. Alright, let's have a go at doing some of these for real, with real values. So here's one that we're trying to find the distance between a swamp. Alright, that'll just have to stay there. That's gone. Trying to find this distance from A to E across the swamp. I know that I have this triangle CBD that I can measure, 36.8, 24, and 40. And I'm trying to find something about this bigger triangle CAE. Okay, this is the one I'm trying to find, that X at the bottom. I know that the distance CA is going to be 73.6, okay, because it's double the distance. See the double dashes means it's going to be double. And I know the distance CE will be double 24, so 48 meters. So if I'm trying to find this unknown here, X, I can say, well, I'm going to choose these 2 sides to be the ones that I'm going to use the similarity of the triangles on. Okay, so the idea will be AE on CE will be the same as BD on CD. And pretty much divide these 2 yellow ones and make it equal to these 2 green ones divided in the same order. I always put the X on top and make it easier to solve. X on 48 equals so we get X on 48 equals 40 on 24, and I can just solve this for X. 40 on 24 times 48. Okay, I'll end up with 80. That's the formal way to do it. Obviously, if you wanted to show that the scale factor, the thing you're multiplying by, is 2, you can just say that the unknown is 40 times 2 which will be 80 meters. Okay, but this is better communication justification. That's the side over here. Okay, and it'll help you solve some of these harder problems as well. Again, trying to find the distance across the river. Yeah, the distance across the river, I don't know it, but I know some of these other measurements that I've been able to measure. So I've got a small triangle ABC with 32 meters, and I want to find this side. I've got a bigger triangle AED, 46, and this whole distance here, all the way across, will be x plus 65. Okay, going x and then another 65. Okay, so the way I'm going to do this is, again, just dividing similar triangles. So I'll grab this side divided by this side. Direction. Similar sides on the same triangle. So this guy divided by this guy, and this guy divided by this guy. So let's do that. AD on DE is AB on BC. It's basically going to end up as x plus 65 on 46 equals x on 32. Okay, from here we'll multiply, cross multiply. 32 lots of x plus 65 equals 46 times x. Do some expanding. All these algebra skills will be coming to help you out. $32x plus 20,080 equals 46x. Need to get all the x's to one side. So from that 46x, I'm going to take 32x. Okay, end up with 14x here, and to get x by itself, we'll divide by 14. End up with 148.57 meters. Okay, that's probably the hardest one of these problems that is there in existence. Okay, problem 3. We've got some congruent triangles. Since these two sides are congruent, I can write a 21.4 on here. Okay, and then I'll be able to find this unknown side using Pythagoras. I'll just call it lowercase x for simplicity. And I say I'm using Pythagoras. Okay, again, this can be A, this can be B, this can be C. Try and do it as formally as you can. So 29.4 squared plus x squared equals 51.2 squared. And you should be able to finish it off from there. There we end up with 41.92 meters. And the final one, there we've got a small triangle and a big triangle. There we've got this small triangle JKH, which we know 29.6. And we've got this bigger triangle LMH. And I want to know this side. And in this case, I can't do any ratios because I only know one side. But I do know that the scale factor is going to be 2. Since they're all double the distance of the previous one. Okay, so you have 1 dash here, 1 dash here, must be double. Double dash here, must be double. Okay, so the unknown side will be 29.6 times 2. Okay, or 59.2 meters. So hopefully you've got an idea of some of the strategies out there. Okay, mainly using Pythagoras, similar triangles, and congruent triangles. Have a got these questions, and if you want more, there's some more in that PDF on the page there. Okay, bye.